Hello, and welcome to the Mechanical Engineering Team 3 and Material Science and Engineering Team 5's Senior Design Project for AeroGear, quench plug for ring gear manufacturing process. Members include Mechanical Engineering students Chris Rowley and John Swanson, and Material Science and Engineering students Brittany Nelson, Nick Simpson, and myself, Ryan Cormier. Assisted by the faculty advisors Dr. Cooper and Dr. Frame, and industry advisors Pat Bruckner, James Janik, and Justin Hewitt. The task given to us by AeroGear was to design a quench plug to reduce ring gear distortion during the cooling process of heat treatment and rapid gas quench. To accomplish this, we had to select a material for the quench plug and ensure said quench plug maintained the roundness and flatness of a roughly 23-inch diameter ring gear during a 7-minute cool down from 1525 degrees Fahrenheit to 120 degrees Fahrenheit, as well as withstand 50 cycles of that same heat treatment.
On the left we have the quench plug and ring gear configuration. The quench plug in orange resides on the inner diameter of the ring gear. We expect there to be a gap between the two bodies such that during the heat treatment process there will be an expansion of the plug, causing an interference between the two bodies. This interference can be calculated using the first equation on the right, subtracting the outer diameter of the quench plug from the inner diameter of the ring gear. We then use this interference to calculate the radial stress on the quench plug, which is equal and opposite to the pressure imposed on the plug by the ring gear. We can use this to then calculate the tangential stress of the quench plug. Altogether, we use these to calculate the maximum shear stress of the material, which can be compared to the yield strength of the material of the plug. This provides an upper limit for the shear stress of the plug. Additionally, we use the critical buckling pressure as another upper limit to help indicate the allowable dimensions of the quench plug.
Using the equations given in the previous slide, we created a thermomechanical analytical model. This model is based on constraints given to us by our sponsor AeroGear, of which they wanted us to be within 5 thousandths of the ring gear at 800 degrees Fahrenheit during the cooling process. They didn't want any interference below 1315 degrees Fahrenheit, and at any given temperature they did not want us to exceed an interference greater than 8 thousandths. In this model, we performed two main analyses. One being the maximum shear stress theory. We used a factor of safety to ensure the design did not fail, and the other analysis was to optimize the strength to weight ratio. To create this model, we used the inputs shown on the slide. Using temperature, we collected outputs in 50-degree increments for both heating and cooling. This ensured we were meeting the given constraints. The outputs gave us stresses. We took the summation of the tangential and diametral stress, made sure it did not exceed the yield strength or the critical buckling load at any temperature. We were also able to see interference at every temperature, which allowed us to adjust the design to make sure we didn't have any premature or excessive interference. Finally, the model gave us quench plug dimensions. This included the inner diameter, the outer diameter, and the thickness. We were also able to calculate the weight based on these dimensions.
Creep is the slow deformation of materials under constant loading or cycles. Due to the number of cycles that the quench plug will be going through, we know that creep failure will be its primary failure mechanism. So we wanted to compare the creep rates of our three alloys. As we see here, we have the normalized creep rate for each quench plug material versus time, with the test conditions shown in the bottom left corner.
Flow stress is the instantaneous value of stress required to continue deforming the material, and flow stress is an important factor in determining the quench plug material. By looking at published data, we didn't see too much for alloy C, but for alloys A and B, we were able to compare how they performed at the same strain rate and temperature. And as we can see, alloy B has a higher flow stress curve than alloy A.
The limitations of the TMA apparatus being used being unable to replicate the cooling conditions of our sponsor, we went with a more mathematical approach. Shown here is the time temperature transformation diagram of the steel we are using mapped to the 7-minute cooling. Using the equations shown here, we were able to calculate the coefficient of thermal expansion for each of the transformations that occur in the steel as it begins to cool. Using the equations for the coefficient of thermal expansion and the equation for volume change shown here, we were able to correctly map the volume change during cooling of the AISI 9310 steel. And as we see here, the volume decreases as it is cooled because metals tend to contract as they are cooled.